Symmetry is a very important part of chemistry, and all molecules that you will come across have one form of symmetry or another. Symmetry is very visual, and you will need to learn to think in 3 dimensions. So having a model kit with you for the workshops in this course will be very useful indeed. There are chapters on symmetry in some of the key textbooks, particularly in Kieran Malloy's book Group Theory for Chemists, which is one of the key textbooks for the course, and also in general texts such as Shriver and Atkins and Housecroft and Sharp. So let's make a start. A symmetry operation is an action on a molecule which apparently leaves that molecule unchanged. And we will show you what this means over the next few slides. Associated with each symmetry operation are symmetry elements, and those are listed below. When referring to these symmetry elements, we will use what is called the Schoenflies notation, and in this notation, the identity, which does leave every atom in a molecule unchanged, is called E. There are axes of rotation, denoted as capital C, and the order of that rotation, that is, the number of times that the rotation occurs within 360 degrees to give you the altered species, is defined by N. Reflection in a plane is also possible, and that's denoted sigma. Inversion through a point, that is taking any atom, moving it through the center of the molecule to a position opposite, leaving it apparently unchanged, is called an inversion. And finally, we have an improper axis of rotation, which we will explain in more detail shortly. So let's look at the identity operator first. This does nothing. All molecules, therefore, must have this symmetry element. And while it may seem trivial, because we are going to develop the idea of symmetry into group theory, it is essential for group theory that there is an identity operator in each group. So if we look at the molecule on the left, applying the identity operator gives us the molecule on the right, i.e. it's unchanged. So moving on to the axis of rotation, where Cn is the n-fold axis of symmetry, we have rotation of a molecule by an angle of 360 degrees divided by n. Molecules may well contain more than one Cn axis, but the axis with the highest value of n is called the principal axis. So again, if we look at the molecule on the left, we now have the molecule on the right, and rotation by 180 degrees leaves it apparently unchanged. So that's a C2 axis. Are there other axes of symmetry in the molecule? Yes, we can have a twofold rotation along the carbon-carbon double bond, as you can see in the top picture, leaves it unchanged, and there's also a C2 axis perpendicular to the carbon-carbon double bond. Rotation around that also leaves it unchanged. So there's some very common molecules that have this rotational symmetry. So we have water on the left, and you can see a C2 axis going through the oxygen atom there, rotates one hydrogen atom into the other. That's a C2 rotation, leaves that unchanged. Whereas on the right, we now have ammonia, NH3, so threefold axis going through the nitrogen atom, as we can see top and bottom there, rotation by 120 degrees leaves the molecule apparently unchanged. So that's the C3 axis. Moving on to BF3, which is the planar molecule, we can see side view looking down from a fluorine to the boron, so along a BF bond, and from above we can see that again 120 degree rotation will leave the molecule unchanged. So there's our C3 axis looking in the plane, and that's the highest order end, so that's the principal axis. And then we also have perpendicular to that C2 axis along a BF bond which rotates the other two fluorines into each other. So there must be another C2 axis in that direction and a third one along there. So we've got a C3 axis as the principal axis and three C2 axes perpendicular to that. So let's move on to reflection. Remember, they're all called sigma, and depending on the orientation of the mirror plane associated with the reflection, we can call them sigma V, sigma D, or sigma H, and we'll explain that. So let's look at sigma V first, and that's reflection through a plane containing the principal axis. So on the left you've got half a water molecule that is reflected, and you see the other half, so there's a mirror down there including the principal axis, and that's labelled sigma V. There's also another mirror plane, also a sigma V, but to differentiate it from the first one we'll call it sigma dashed V, which is a mirror containing the three atoms of water, and the front half of each atom is simply reflected into the back half. Again, moving on, let's look at a sigma H. That's a mirror plane perpendicular to the principal axis. So an example of that would be xenon tetrafluoride, which is square planar. So looking down from above, we can see that there is a principal C4 axis there, and C2 axes along the xenon fluorine bonds, and also between them, as you can go down the C '2 axis there, and that rotation will rotate two of the fluorines into the other two. But we also have a mirror plane, as you can see on the right hand side there. It's a horizontal mirror plane. It lies in the plane of the xenon and the four fluorine atoms, and is perpendicular to the principal axis. The inversion is the projection of atoms through a centre of inversion. It's not the same as a rotation, and here we've numbered the hydrogen atoms to illustrate what we mean. So the centre of inversion is the little plus sign in the middle of the molecule on the left-hand side. Operating the centre of inversion moves hydrogen 1 to hydrogen 4 and hydrogen 4 to hydrogen 1. Similarly, hydrogen 2 goes to hydrogen 3 and hydrogen 3 goes to hydrogen 2, as you can see on the right hand side. And that applies to any molecule where there's a centre of inversion.
So the final type of symmetry operator is the improper rotation. So I'm going to recommend you build yourself a model of methane and arrange it in such a way as the two legs at the bottom are kind of splayed outwards and the two legs at the top, one's towards you, one's away from you. Now the first thing we need to do with an improper rotation is rotate the molecule through however far. In the case of methane, this is an N4 or a 90-degree rotation that we're going to do. So if we rotate the molecule through 90 degrees, now the legs at the top are displayed and the legs at the bottom, one's towards you, one's away. The next step is to have a reflection through a plane perpendicular to the rotation axis. So something that people sometimes forget. The perpendicular to the axis is really important. And now we can see that having completed the rotation and then the reflection, we end up with a molecule which looks essentially the same as what we started off with. And the molecule is apparently unchanged. Any molecule with a sigma H plane perpendicular to this principal axis also contains an SN, improper rotation element.
So we've got all this information. If you're given a molecule, how can you work this out? Well, there's a systematic way of doing it, and that's shown on this chart. And don't worry, we'll give you a copy of this chart on paper so that you can go through it, and it's fairly legible, but you use this chart to establish the symmetry of any given element. So let's have an example of that. So let's think about cyclopropane, and we ask through the chart a series of questions, and from that we can work out what the symmetry operations that describe that molecule and what its point group is. So let's start with cyclopropane. Is this molecule linear? We've got a choice of yes or no, and I'm sure you'll agree that the answer is no. So we can move across. Does this molecule contain two or more unique C3 axes? The answer is no. Does the molecule contain a proper rotation axis, Cn? So if we think of cyclopropane, the answer is going to be yes. So we need then to identify the highest order axis and establish whether there are other axes perpendicular to that. And we can go up because the answer is that we've established the highest order axis, and the molecule does contain a mirror plane perpendicular to that axis because it's a C3 and we've got a sigma H perpendicular to it. So we can answer yes to those questions, and the point group is of the type DNH, and for cyclopropane it's D3H because the principal axis is a threefold. Okay, next one, ethanol. Is this molecule linear or not? Well, again, the answer is no. Does the molecule contain two or more unique C3 axes? So the answer is again no. Does the molecule contain a proper rotation axis? Think of ethanol. The answer again is no. Does the molecule contain a reflection plane? Yes, you can get a reflection plane through the oxygens and the carbons, so the answer is yes, it does. So that's a low symmetry molecule, and it's defined as CS. And then we can think of two crown ether complexes, either an 8 crown 4, so you remember they're 4 oxygens forming an 8-membered ring with carbons, or 12 crown 4 with, again, 4 oxygens, but now 2 carbons between each oxygen. So again, is this molecule linear? No. Does the molecule contain 2 or more unique C3 axes? No. Does the molecule contain a proper rotation axis? Yes, it does. You have one pointing down the middle of the molecule. So we need to identify the order of rotation there, and the order is going to be 4 in that case. So then we go on through that. Does the molecule contain a horizontal reflection plane? No, there's puckering. So we go to no there. Does the molecule contain vertical mirror planes? So the answer is yes. So it's a CNV, and in this case that would be a C4V. And last one, linear molecule. So this time we go to the right. It is linear. Does the molecule contain a center of inversion? So there's a center of inversion midway between the 2 carbon bonds. So the answer is yes. And we have the point group D infinity H, which is special for linear molecules and easy to identify. So we have all these potential routes, and by using this method you can actually work out the point group for each molecule, and we'd like you to have a go at this during the rest of this lecture stroke workshop. But just before we move on to that, I want to say a little bit more about a component of symmetry that's very important, and that's chirality. Because again, chiral molecules are very important in pharmaceutical chemistry and in catalytic chemistry and many organic and organometallic reactions. So let's just remind ourselves what chirality is. It's been described previously as a molecule that contains an asymmetric carbon. So central carbon blue there, 4 different groups. From the symmetry point of view, a chiral molecule is one where its mirror image is not superimposable. And a chiral molecule rotates the plane of polarized light, so it's said to be optically active. And it exists in 2 forms, a plus form, delta form, that rotates the plane of light clockwise, and minus or L form that rotates it anti-clockwise. If you have 50-50 mixtures of these, you get a racemic mixture which doesn't rotate polarized light. But just from the symmetry point of view, a molecule is chiral if it does not contain an improper axis of rotation. So molecules with asymmetric carbons only have the identity operation E, so they must be chiral. And you'll remember from earlier on that SI is equal to a mirror followed by an S2, which gives you the centre of inversion, so that any molecule with a plane of symmetry or a centre of inversion is not chiral, achiral. Some molecules with symmetry are chiral, hydrogen peroxide for example, but it can't be separated into two enantiomers because it exchanges too quickly. But octahedral metal complexes with bidentate ligands have C3 axes and three C2 axes, and you can see them, an example on the top left of this slide, and those two molecules are not superimposable on their mirror images, and you can see they're defined as D and L forms there. Tertiary amines have rapid inversion, so you can't separate them into their pure enantiomeric forms. So I hope that's been useful as an introduction to symmetry. What we'd like you to do now is go through the problem sheet and see if you can work out the symmetry of the sum of the molecules. Thank you.